All right, let's talk through one of the harder examples that we can possibly have for a multi-unit balance. So what I want you to do is make sure that you open up the student version of the notes for this extraction and distillation process. And I want you to read through this problem. Okay, there's a lot going on here in this particular problem. So the first thing that I want you to do is just read through it to try and understand what this process is. This is a very typical chemical engineering style of problems, but if you're interested as an environmental engineer in finding out how to really optimize systems, you're going to need to know how to solve these types of problems. All right, hopefully you took a pause and read through the question. And we want to, in this particular video, set up our flowchart. So, something that we're going to do in this particular problem is we're going to combine each of the mixers and settlers in the problem statement into a combo, and we're going to call this an extractor for this particular system. So, if that's the case, we're going to have something coming into extractor one from one direction and another, an effluent coming out and going into extractor two, and then another effluent that comes down into a mixing point. We have an input into extractor 2 and an effluent from extractor 2, and then another stream that comes into this mixing point. After they hit this mixing point, we go into a distillation column, which is going to have two different streams coming out. So what I've done is I've copied over all of the numbers from the previous side of this paper that you're given in the problem statement, and I've numbered all my streams. So I've gone pretty much clockwise and then down. So what I've done is I've labeled all the streams. The next thing that I did is I drew all of the system boundaries that are possible in the system. So I drew in blue the overall system boundary. I drew a boundary around extractor 1. I drew a boundary around extractor 2, around the distillation column, and around the mixing point. So that tells me how many different systems I can possibly use to solve. So you can see that there's 10 streams. That's a lot in order to solve for. So we're going to have to be very strategic about how we go about solving this problem. So one of the first things that we're going to want to do is we're going to want to say, all right, let's use acetone, water, and our solvent. And let's say A, W, and M for those so that we know what we're talking about. And we're going to use a basis of calculations of 100 grams of acetone water feed. So that's what's coming in right here. This M1 is our basis of calculation. There's only acetone and water, and it's half and half coming in, so it makes sense right here to use that as our basis of calculation. All right, so we have a simplified and labeled flowchart, right? Completely labeled. All right, then let's determine the boundaries where balances can be written. So we can write mixing point, we can write extractor 1, extractor 2, the distillation column, and then here's the one that's kind of interesting and different about this problem. We can actually write a boundary around the combination of extractor 1 and extractor 2. So we can actually, I didn't draw it on here, draw a boundary around extractor 1 and extractor 2, which makes number 3 internal to that system. So that's another option that we have here. And then we can write one on the overall system. So that's going to tell us that we have 6 different boundaries or 6 different systems. And we have 3 different species, A, W, and M. So there we are. Flowchart is set up, boundaries are drawn, now we can start moving forward. So let's start with our degree of freedom analysis so that we can have a strategy going forward. I'm going to show an example of one possible degree of freedom analysis, and then I recommend trying the others yourself and checking against what I'm going to show. It's good practice for degree of freedom analysis. So on the overall system, let's write our degree of freedom analysis. If we look at the overall system with our blue boundary up here, we have an unknown coming out in 10, and we have an unknown coming out in 9. We don't know what's going on there. So we've got 5 different unknowns, 2 different masses, and then the composition of that 10th stream. We've got 3 species, A, M, and W, which means that we have 3 independent balances we can write. And then we have one relationship. We know that the sum of all those mass fractions equals 1. So that's going to give us 1 degree of freedom, which means that we actually need one more equation in order to solve the overall system. So right now, looking at the overall system boundary is not going to help us. So again, my recommendation is that you try these on your own, but something similar is going to happen as we start to go through the other systems. We're going to find on extractor 1 that we have 2 degrees of freedom. On extractor 2, we have 1 degree of freedom. The mixing point, we have 3. And the distillation column, we have 4. So we don't have enough equations to solve for any of these. That's a problem. But remember, we have one more system we could use, and that's the combination of the 2 extractors. In this combination of 2 extractors, we actually have 3 unknowns. We have M6, XM6, and M7, and we have 3 species. So we actually have 0 degrees of freedom, and this is solvable. So what this is going to tell us is that if we want to find a solution to this problem, we're going to have to start with this combination of 2 extractors and see what that gives us before we move on to the other systems. So, as part of your pre-lecture for today, I want you to take this setup, make sure that you understand it, and then see how far you can get to a solution. What you're going to upload to Canvas is the attempt that you make at this particular solution.